Okay, so let me then refresh you if you're saying you forgot on how to use Laplace to solve this. Okay?
Well, would this, is that,
You'd have to first take Laplace of both sides. No, we don't want to use the definitions here, too long. We look, watch. What? We're going to take the Laplace of the right-hand side of each single term, okay? Laplace of a sum is the sum of Laplaces. So minus the Laplace of y equals the Laplace of e to the 3t on the right-hand side, okay? Now,
right.
the Laplace of dy over dt, as we covered in the previous section, or at this point you can look it up in the table, right? The Laplace of a derivative is where did it go? The let me show you where the definition is. It's right here. It's equal to s y of s, okay, minus the initial condition y of 0. So this is first order. You need one initial condition, which you have at y of 0 equals 2. Okay? Minus the Laplace of y is just always y to the s. We are after y to the s. So basically an overview is we are figuring out what y of s is by doing Laplace. And then once we have y of s, we do inverse Laplace of that, and that gives us y of t, which is the solution for the differential equation. Okay? So equal. Now we go on the right-hand side. The Laplace of e to the 3t, you look in the table, right? E to the at is 1 over s minus a. So a in this case is 3. So it'll be 1. So the Laplace of e to the 3t is 1 over s minus 3. Okay, now y of 0 is 2. So I can replace y of 0 with 2.
Yeah.
Okay, and I could factor from these two y of s. So then I would get s minus 1 times y of s minus 2 equals 1 over s minus 3. And now it's just algebra to find y of s. So y of s will just be 1, or let's do it in 2 steps. So s minus 1 times y of s is equal to 1 over s minus 3 plus 2. Yeah. And you can find a common denominator here. So this is just, if I s minus 3, so this becomes 1 plus 2. You multiply the 2 times s minus 3, so 2s minus 6 over s minus 3. And then this becomes 2s minus 5 over, because 1 minus 6 is minus 5, over s minus 3. So therefore, y of s is equal this divided by s minus 1. So that's 2s minus 5 over s minus 3 times s minus 1. Okay? Now, this is y of s. The objective is to take inverse Laplace transform of this.
Right.
But to be able to do the inverse Laplace of this, so you do inverse Laplace on the left, and you do inverse Laplace on the right. But this needs partial fraction decomposition to find the inverse Laplace, because you need to separate it into two different things. Okay? So let's work it out separately. Right? So I'm going to call here this equation 1, move on, I'll come back to it. S minus 3 over s minus 1. So this is just a over s minus 3, no? Plus b over s minus 1. And now the objective is to find what those a and b are. Okay? So now we're going to do a common denominator. So a multiplies the s minus 1, and the b multiplies the s minus 3 over s minus 3 times s minus 1 equals the original. Okay? And of course the denominators go away because they're the same thing.
All right.
FOIL in. So as minus a plus bs minus 3b equals 2s minus 5. Already? Collect the ones that have the s. So that's a plus b times s minus a minus 3b equals 2s minus 5. Now, for those two polynomials to be equal, what multiplies the s here has to equal what multiplies the s here. No? And the constants has to equal the constants, which necessitates that a plus b equals 2 and minus a minus 3b equal minus 5. Right? And you could just add these two to solve for a and b. So if you add these two, go away, and you get minus 2b equals minus 3. No, 2 minus 5 is minus 3, which makes b equals 3/2. No? Plug it back in the first equation. So then we get a equals 2 minus b. So that's 2 minus 3/2. So what's that? 4/2 minus 3/2, 1/2?
Yeah.
So a is 1/2. So now I go back and plug those into equation 1, which is here. Okay? So substitute into equation 1. So the inverse Laplace of y of s is just y of t, which I'm after, the solution. Yeah. Okay? And okay, so this became this, right? Because I did partial fraction decomposition. Okay, so now instead of plugging here, I will just plug in here and separate them, take the inverse Laplace of each one. So this is inverse Laplace of a, which is half over s minus 3 plus b, the inverse Laplace of b over s minus 1. So b is 3/2 over s minus 1, and we're going to take the inverse Laplace of that. Okay? Now, half is just a constant, so it comes out. Inverse Laplace of 1 over s minus 3. Yeah? And 3/2 is a constant, it comes out. Inverse Laplace 1 over s minus 1. And if you look in the table, the inverse Laplace of 1 over s minus a is e to the at. So this becomes half e to the 3t. No? And the same thing on the other one. 3 over 2. 1 over s minus 1 will be, the a will be 1, so e to the t. So this is yt, which is the solution for the non-homogeneous differential equation that we started with using Laplace. Okay? So this is how you use Laplace transform to figure out the solution of this non-homogeneous differential equation. Before, we had used either separation of variables, which you can't do here. This is non-separable. Or you could use here, see if it's exact. And if it's not, make it exact, then using the integrating factor. That's how we used to solve this. So the advantage of this on the test, if you forget on how to do it using any of those methods that we've learned initially, you can do it using Laplace. And with the initial condition, Laplace will get you that general solution of the non-homogeneous. Because for the, if you remember, for the homogeneous, you had to also go and do either undetermined coefficients of variation of parameters. So on this problem, it would have been longer to probably, well, not if you use the integrating factor, actually. Probably about the same time to solve it using other methods as Laplace. But, you know, but of course, Laplace doesn't come free. At the same time, you saw we had to do partial fraction decomposition. And so you need to be pretty confident in doing that. And then you have to know how to use the tables. Okay? So you want to try one?